session we'll do few problems on concurrency and see the different other synchronization primitives like monitors, so on. So let us solve this problem. In a multi-programming environment, a single dispatch list may be accessed by multi-processor dispatcher. Give an example of race condition that can occur if two dispatchers access the dispatch list concurrently. In a multi-programming environment wherein more than two processes can reside into the memory simultaneously, and we know that race condition is nothing but if two processes are trying to access the same resource, they are competing for the same resource simultaneously. Now, in this we have to demonstrate a situation wherein because of this concurrency, because of race condition, even though you are having a multiprocessor environment, both of the processors are executing the same process, thereby inefficient utilization of the CPU. Because if you have two CPUs in a multi-programming environment, if you have n number of CPUs, then the best utilization of this process, this environment is to allow n number of processors to execute simultaneously, because you have n number of processors. Okay. Now, so generally what happens, how a process gets executed. Okay, in dispatch table you have now there are actually few steps for executing a process. Okay. First is a processor will get the pointer to a process. Okay. So it gets pointer to a process from the process dispatcher list. So this is this pointer is pointing to a process to which it has to execute on its processor. Okay. And this dispatch, these pointers are maintained in a dispatcher list, and this dispatcher list is shared across all of these processors, CPU 1, CPU 2, and CPU 3. Now the problem here is, suppose if all of these processes are given chance simultaneous to see this dispatch list, dispatch list which is shared among all of them. So all of them will see the next process to execute is suppose this X. Okay. So all of them get a pointer to this process and they will update this pointer and executes process and executes the process. Okay. Now when three of the CPUs are seeing the same seeing the same process address, and all of them will update the pointer to the same process, and both of these or three of these CPUs are executing the same process, which is P1. The efficient utilization would be if CPU would be executing process Pi, CPU 2 would be executing the process Pj, and CPU 3 would be executing the process Pk. But here what is happening is, because of this concurrency, all of this CPUs are executing the same process. Okay. Now it is possible. So let's give this is the situation in which it happens. So what happens is, for example, this is for CPU 1. Okay. I'll just discuss it for two CPUs, and we can extend the same concept for CPU for three CPUs as well. This is CPU 1 and this is CPU 2. So assume that both of them are seeing. So instruction 1, because they are multiple processors, so both of these processors you will see and gets the pointer to a process. This is time t1, this is also time t1. Then at time t2 also both of them update the pointer. Okay. And t3, both of them are executing the same process. So this is the example of race condition where multiple processors in a multi-programming multiple processors are executing the same process, even though you are having n processors. It is because of race condition. Okay. So now I'll solve few problems and see. We'll see some code, okay, which is exposed to race condition, and we'll see how to solve this problem. Okay. So let's take an example. We'll write one pseudo code and see whether shared resource has any problem in race condition, and we'll also see solution how to solve those race conditions, how to solve the problem of shared resource, so that if it is allowed to execute on a uniprocessor system or on multiprocessor system, there should be no data inconsistency. The shared variable should not be in an inconsistent state. Okay, let's take an example. We'll take an example like this. Okay, suppose I have one process P1, okay, and another process P2. Suppose this process P1 increment the value of count, and there is one variable called count. Okay, so this variable is shared between these two processes. So whenever increment gets called, then process P when increment gets called, then increment process will increment the value of count by 1. Okay, and what is another process is doing? Another process, it checks the value of count. Okay, if the value of count is greater than 5, then it prints that the value of count is greater than 5, and it tries to decrement the value of count. Okay, but if the value of count is already 0, then it returns 0. Okay, or if the value of count is neither 0 nor greater than 5, then it returns 1. We are just taking an example of this process, okay, and see is there any problem of race condition or not. Okay, so let's write code for process increment. So void increment void. So here it will check if value of count is greater than 5. What it does, it prints, for example, PF means printf, count is greater than 5, which is equivalent to %d count. Okay, and it prints that the value of count is greater than 5, and it decrements the value of count. Count is equal to count minus 1. Okay. Otherwise, if the value of count is less than 5, then increment should increment the value of count. It means the process if the value of count is 5, then increment will not increment. It actually decrements the value of count. And otherwise it sets the value to be 1. It means it is incrementing the value of count. We will say count is equal to count plus 1. And we have another process, okay, void decrement. Now here we will have one loop, for example, while true. So here I define true to be 1, is a non-negative, it's a non-zero number. Now here it checks the value again. If count is greater than 5, okay, then it also prints the value of count is greater than 5. Okay, and then it reduces the value of count is equal to count minus 1. Else it check if count is equal to 0. Okay, if the value of count is already 0, it never takes the negative value. We are assuming that. Okay, so it returns 0. Else it means if the value is neither greater than 5 or not less than 1, not less than 0, then it returns 1. Okay, it returns 1. So where it is returning count. Now, if I execute this return inside, so at end I will return it. So, here I am returning for example. So, now how do we synchronize them? Okay. So, use either semaphores or mutexes for solving this problem. So, we can solve this with any of these primitives. Okay. Suppose if you are using C, then C can solve this. C supports actually semaphores and mutexes. So, for that we have to include one library called hash include pthread.h. Okay. Now, inside this we have to declare one mutex. Okay. So, pthread underscore mutex, pthread underscore mutex underscore t. I'll just write this. I'll write the solution. I don't have space here. So, we'll write here. Suppose is main. Inside main we do write pthread underscore mutex underscore t. Will declare one mutex and we call it as lock on count, lock on count, lock on count, which is equivalent to pthread underscore. So, pthread underscore mutex underscore initializer. All are in uppercase. Okay. Then now, in this entire code, whenever you are trying to access the shared resource, before that shared resource, okay, we have to write this line. Okay. You can solve this as you have already taken this code. You can just, whenever you are trying to access this count, before you access this count, okay, we have to write this line pthread underscore mutex underscore lock ampersand lock on count, lock on count. Okay. Now, after doing it works like wait. Okay. So, now perform all the modifications. When modifications are completed on count, then after releasing this shared resource, we have to write pthread underscore mutex underscore unlock now. Lock on count. So, we have to lock before we access count and unlock before we access. For example, here we are accessing count, lock it, here unlock it, locking it, unlocking it. So, before we use this shared variable, we have to lock them first and unlock. Now, here if else it gets run, so you have to lock, okay, unlock at end. Okay. Similarly, in this code, whenever you are access count, lock them. After we access the resource, we unlock them. Right. Now, we will see we write C code, it becomes big and we do not have sufficient board. We will take pseudo codes and try to solve with synchronized primitives, signal and wait. We will take one of the one more process, for example, a process P1. Okay. Now, this process P1, suppose we have a shared variable called int x. Okay. And here we have an infinite loop which is working, and in this loop we are declaring the value of okay, what are we doing is we assume that the value of int is initialized to 10, for example, or is equal to 10, suppose. Okay. Now, here we are incrementing, we are first incrementing the value of x. So, x is equal to x plus 1, okay, and x is equal to x minus 1, okay, and I am checking if x is not equal to 10, pref x is equal to percentile d x. Suppose this is very important question for understanding problems with currency and how to solve it. Now suppose I have this pseudo code, okay, where a shared resource called x is shared between all of this process, and you tell me when we execute this process on single CPU sequentially, will ever this printf prints x is equal to 10? It never prints x is equal to 10. X is equal to 10 will never be printed. What I want is, assume that if multiple processes are executing the same code, okay, and we assume that in universal system pseudo parallelism is allowed, then show the sequence of execution of instructions which prints the output x is equal to 10. Okay. Now, when you see the code, x is equal to 10 will never be printed, because whenever the value of x is not equal to 10, then only you are printing. Okay. So, but because of this pseudo parallelism, if you allow pseudo parallelism, then it is possible that x is equal to 10 gets printed. So, we have to show the sequence of steps which prints x is equal to 10. So, here what do we do is, assume that I have two processes executing and they are in pseudo parallelism, means they are executing by interleaving the CPU, because we have one process, okay, that is called pseudo parallelism, and there is chances of because of race condition the shared variable may be left in inconsistent state. Suppose, okay, now this is the same code, this process P2 is having the same code, for example. Okay. Now let us write the sequence of steps how process P1 and process P2 executes, which results in x is equal to 10 to be displayed. Okay. Now in time t1, for example, now I just mark it as equation 1, equation 2 and equation 3 and equation 4. Okay, these are 4 equations. So assume that first at some time I, or take time 1, instruction 1 has been executed. Okay. So here you will have for example memory context. Okay. So at time 1 x is equal to x plus 1, the value of x was initially 10. Okay. For some time, for example for time I, we take for initial time t, okay, t1, the value of memory to be 10, okay, and assume that ti plus 1th instruction, okay, and this okay, equation. So I assume that, just I am leaving this, these are also instructions, but we assume that we are starting from here to focus on what are the problems with concurrency, right. So at time t, we know that the process sees the value of memory to be 10. So initially the value of memory was 10, okay, and when first instruction is executed, okay, when first instruction is executed, then which is x is equal to x plus 1, then value of memory contents will be given to 11. So it has been modified. Now when it has been modified, then assume that another process has executed t2, okay, instruction 2 has executed. Now it makes the value of x to be x is equal to x minus 1. So when it makes x is equal to x minus 1, again the value of the value of 10 becomes what? 11 becomes 10. Okay. Now it checks at time 3, it checks it executes instruction 3. When it executes instruction 3, so if x is not equal to 10, no, x is not equal to 10. No, we are not getting, so it doesn't print. So what we do is, okay, now assume that after executing this instruction, x is equal to x plus 1, interrupt has occurred. There is an interruption. when interrupt comes, what happens? This process P2, okay, at some time T2, okay, it will also execute instruction I1. When it executes the instruction I1, this is actually our critical section. This all the code which is acting on a shared resource is critical section. So now I1 is when I1 is executed, okay, so the value of x1 will be 12 here. Okay. The value of x1 will be 12, and when once the value of x1 is 12, then and time T3, then instruction I2 will be executed. It makes the value of 12 to be 11. Okay. Now in time T4, for example, instruction I3 is executed. If instruction I3 is executed, now it is true that the value of memory contents here. Okay. Now, okay, I am sorry. Here it has to be 12, it has to be 11. Here what am I doing? X is equal to x plus 1, and here we are doing x is equal to x minus 1. Okay. Because it is shared, they see the values here. When it sees I is equal to I plus x is equal to x plus 1 and x is equal to x minus 1, then instruction at time T, when instruction I3 is executed, it checks the condition, if x is not equal to 10. Now this is true. Okay. So now when this is true, okay, it enters into the if. When enters into the if, again assume preemption occurs. When again preemption occurs, what happens? This process will be given chance. Process P1 will be given chance. So in time T5, okay, now it will resume its execution. So it will execute instruction I2, which is actually x is equal to x minus 1. Now it is very easy to show that x is equal to 10 gets printed, because here we are having language level instructions, but it is also possible to break again these high level instructions into lower level instructions. Our code becomes bigger. So it is possible to prove this race condition is possible, which prints x is equal to 10 with these instructions as well, because we are splitting it like this. So when it does x is equal to x, I2 is x is equal to x, and then value becomes 10. When value becomes 10, assume that interrupt can be occur at any point of time. When again interrupt comes, then again chance will be given to process P2 at time T6. Okay. At time T6, here instruction I3 was executed, okay, and it has entered the if statement. Now instruction I4 will be executed. When instruction I4 will be executed, okay, it has to print the value of x, but in memory the value of x is 10. Okay. So it prints x is equal to 10. This is happening because of race condition. If you execute this code on a system, it never prints x is equal to 10 because of this condition, but because of pseudo parallelism, it is printing x is equal to 10. Now it has to be controlled. Okay. How do you control this? Okay. How to rewrite this code in order to avoid mutual exclusion? So now here, whenever I access here, okay, I declare one variable got, for example, semaphore mutex is equal to 1. So wait on mutex, okay, then signal on mutex. So this will solve all problem. Now process P1. Now these are all atomic actions. When process P1 to the critical section, it performs mutex, which gives value of mutex to 0. Another process want to execute, it has to wait till it does something with this critical section. Okay. When it comes out, it again signals again, which gives the value of mutex to another process P2 will be allowed to enter into critical section. So here actually this we provided solution for this, but actually the question, you show me the sequence of instruction which prints x is equal to 10, which we have shown already. With the, if the solution is written, then however you execute, you never get it. We have achieved here two processes. Okay. So now we'll see another problem. Called reader writers problem, or I'll give this as an exercise to the audience to solve this readers and writer problem, wherein I'll just give you a few hints and you try to solve this. Now I'll write which is which is prone to concurrency problems, then you try to write the code which will avoid this concurrency problem and the shared resource in a consistent state. So in a reader writers problem, we have reader, n number of readers and one writer. Assumption, our assumption here is, assume that we have one writer which wants to write, and there are n number of readers which want to read. Now there is a critical section here. Okay. We have a critical section. Okay. Rules are like this. If writer want to enter into the critical section, so writer enters the critical section to modify the state of a shared resource. Okay. So whenever any process is modifying the state of a resource, no other processes are allowed to enter into the critical section, because according to the principles of mutual exclusion, okay, we should not allow two processes to enter into the critical section. Right? So which gives you very awkward results, right? So writer, when it has entered the critical section, no other resources or no other processes are allowed into the critical section. So this condition we should make sure of. Okay. Now assume there is, if another reader process wants to come and enter into the critical section. Okay. Now reader process, when it enters into the critical section, it is only reading the state of the resource, it is not modifying, so it should be allowed. But when the writer is already entered into the critical section, the reader process also has to be stopped from entering into the critical section. Okay. Second, suppose you have critical section, one reader process has entered into the enter into the critical section, it has desire to enter into the critical section. If there is no process in the critical section, then reader process R1 has to be allowed to enter into the critical section. W1, assume that it's a writer process. So when another reader process, which is R2, gives it desires to enter into the critical section. Now because these reader processes are only reading the status, they are allowed to enter into the critical section because they are not modifying the state of the resource. Okay. So R2, it means when once a reader process entered into the critical section, there is no restriction on any reader processes to enter into the critical section. But now in this case B, if a writer process want to enter into the critical section, okay, now there is a chance of this writer process may change the state of this shared resource, and few of the reader processes may have noticed and few of them left unnoticed. Okay. So because of this, when reader processes are already in the critical section, no more writing process is allowed into the critical section. Okay. Now here writer process has to wait. Okay. And here reader processes has to wait. Now remember, I am giving you, in order to solve this, you maintain one shared variable called read count. Okay. So I'll give you pseudo code, right? Suppose this is integer int. Okay. Now you have a process void writer. What does it do? Whenever a process want to enter into the critical section, it enters into the critical section, okay, and it exits the critical section. That's all. Because writer process has nothing to do with this. And whenever you have reader process, okay, when this reader process want to enter into the critical section, it enters into the critical section, but before it enters into the critical section, it has to modify the value of read count, and we initialize the read count value to 0. So it will make read count is equal to read count plus 1. I'll write it here. Okay. So void, this is writer process and this is reader process. Okay. Read count is equal to read count plus 1. Okay. After doing this read count plus 1, it will enter into the critical section. When it is leaving the critical section, it makes read count is equal to read count minus 1. Now read count always maintains the number of processes which are reading, which are in the critical section. Okay. Number of reader processes are in the critical section will be given by read count. Okay. Now you write code, okay, should ensure a mutual exclusion here. It should ensure that the value of read count should not be left in an inconsistent state. You have to write a code in such a way that when a writer process is in the critical section, no more reader processes are allowed. If reader process in the critical section, no more writer processes are allowed. Okay, how do you write? I am leaving this as an exercise. So here till here we have completed this concurrency problem with the help of semaphores. Now we have another synchronization primitive called monitor. So what is monitor, and why do we use monitor? Do C support monitors or not? We'll see now. So monitors are already discussed in e-learning. So here I will give you just brief overview of monitors. Monitor is actually a higher level synchronization primitive. Now the basic idea behind monitor is, okay, in a monitor, all the regions, like all the critical sections will be into this monitor, and in a monitor at a time only one process will be allowed to enter and execute the critical section, and when that one process has entered the monitor, then after executing this critical section, it has to leave the monitor. It means it has to leave the critical section. So when it has entered into the critical section, when it has entered into the monitor, then no other process, those other processes which want to enter into this critical section, they are not allowed because of this monitor. Now because of this monitor, the basic idea behind monitor is all the code which is shared, okay, will be moved into the monitors. Because of this idea, the parallel programming was achieved less error prone to concurrency problems, okay, because all the concurrency code, all the critical sections can be moved into the monitor, and the drawback of this monitor is it is not supported by C, okay, but the advantage is it is supported by Java, it is supported by .NET, C#, .NET, it is also supported by Pascal Plus and concurrent Pascal, but it is not supported by C. So now good thing is, with the monitors we can do parallel programming which are very less to error prone, and with the help of semaphores also you can achieve mutual exclusion, you can achieve process synchronization. But again these two synchronization primitives also have few drawbacks. What are those drawbacks? The semaphores and monitors, okay, they can be used for process synchronization only in uniprocessor system or in multiprocessor system. But when you go to distributed systems, they cannot be used for process synchronization. Okay? So here they are, when architecture moved from uni to multiprocessor, they are good. Semaphores and monitors are good. But when it goes to distributed system, that doesn't work. Okay? So this is what about monitor. So just again I summarize, monitor is a higher level synchronization primitives wherein all the shared code will be moved in and only one process will be entered into the monitor. So generally if you want to enter into the monitor.enter method in C#.NET is used, like monitor.enter. So you enter into the monitor. Now after working on the shared resource or critical section, then you execute monitor.exit. Okay. These are the methods which are used for monitors. Now we'll start another topic called memory. So memory also plays very important role. What is memory actually? Memory is actually used for storing temporary results of CPU. and it's a volatile, meaning when power goes on, all the contents of this memory will be erased off. There are two types of memories. Okay, one is internal memory and another is external memory. Okay. Now, apart from that, we'll see this. We have, for example, we have a CPU. Okay. Now, CPU, we know that in CPU we have three parts. CPU has been divided into arithmetic and logic unit, memory unit, and control unit. The registers are nothing but your memory unit, and you have RAM, which is an external to this CPU, we call memory. Okay. Now, memory can be RAM, or it can be ROM, read-only memory, random access memory, EPROM, electrically programmable read memory, EEPROM, electrically erasable programmable read-only memory. There are many of them. So this is a volatile memory. This is non-volatile. Actually, at the time of manufacturing the system, the manufacturers will put some information, and also they install this bootstrap, meaning to start when you install an operating system into the hard disk, right? In any of these active partitions, what happened is, where this operating system is sitting into the main memory, okay, it's sitting in secondary storage. This bootstrap will be loaded into the main memory. From memory, it goes to the disk and bring that part of the operating system into the memory, and thereby your memory starts, your system starts booting. Okay, so the bootstrap is stored in ROM, and the circuit is set up in such a way that when we turn on the system, then bootstrap loader will be automatically is there in non-volatile memory called ROM, will be loaded into the memory, which is RAM, and that code gets executed, which goes to the hard disk and brings the output which is sufficient for booting the system, meaning for making system up. So memory unit is the place where CPU reaches very quickly. Then Then after this, the next place where the memory, the CPU can reaches quickly is memory. Now, after this memory, you can have storage devices. Okay. So it means CPU takes a lot of time to access what is there, storage, but it never accesses it directly. If there is one item which is sitting X in the hard disk, first it has to be loaded into the memory. Then from memory, your CPU can read it. So CPU cannot read data directly from the hard disk. It has to be first it has to be first the CPU first goes to memory unit. From memory unit you'll have memory. From memory it has to be loaded into this RAM, and from RAM it will be loaded into the CPU registers, right. So the hierarchy is like this. CPU, the order in which the CPU can reach quickly is first registers, then CPU can reach, after registers it moves to cache, then it moves to memory, then it moves to storage, or hard disk or tape disk, so on. Now, we are not talking about the organization of storage. We are talking about this memory, how to utilize this memory efficiently and effectively. The goal is how do we allow multiple processes to reside in a system. So by default you have a single, earlier models have uniprocessor, uni partition model, in which only one job is allowed to enter into the memory, and that job will be executing. When that job has completed its execution, then it will be swapped out, and another process will be loaded into the memory and starts executing. That is called single partition method. In single partition method, you have an operating system. Okay. Now this operating system can be at higher addresses or it can be at lower addresses. So when generally it is at lower addresses. So 0, and here we move to n. So now actually this memory is divided into two partitions. One partition only operating system resides, which is of course needed, and remaining memory will be used for a job or a process. Now assume that the size of this memory is 60 kilobytes, and the amount of space is taken by the operating system. We are assuming it's 10 kilobytes. Okay. So remaining will be 54 kilobytes left. Now if a job of size 50 kilobytes want to load into the memory, then what happens, 50 kilobytes job 1 will be loaded and 4 bytes of the memory will be wasted here. Okay. And assume that if I have another job 2, okay, whose size is 20 kilobytes, I have another job 3 whose size is 15 kilobytes. Okay. And assume that this job has been completed. When job 2 is loaded, out of this 54 kilobytes, 20 kilobytes will be used and remaining will be 3-4 kilobytes left. Now, is it possible to run this job J3 in this? Yes, it is possible, but because it is a single partition, the memory, the memory here provides only single partition method, wherein only one job will be loaded into the memory. There is no concept of loading another process. So, thereby resulting in internal fragmentation. So, what do you mean by an internal fragmentation? Internal fragmentation is wastage of memory which is internal to the partition. Okay, there are two types of fragmentation. One is called internal fragmentation and another is external fragmentation. So, which is external partition is called external fragmentation, and the wastage of space which is inside the partition, which is in this case, okay, is called internal fragmentation. We will see the cases wherein we will get external fragmentations as well. Now, here this scheme has few drawbacks. Okay. There is inefficient utilization of memory because you have 56 kilos of memory and we have two jobs which can be accommodated in memory simultaneously, but because of this single partition technique, no two processes will be able to enter into the memory. It means there is no concept of multi-programming in single partition method, which is actually an inefficient utilization of CPU. Okay. So, there we moved from single to multi-partition technique. So, now let us see what you mean by multi-partition technique. Multi-partition technique. Now, actually there are three schemes in multi-partition technique. Okay. The first scheme is dividing the memory into n partitions, and each partition is of size and every partition is of equal size. Okay. So, dividing the memory into equal size partitions. Now, let us take an example. Suppose I have 64 kilobytes of memory. Okay. I am taking an example. Okay. Now assume that this memory has been divided into 8 partitions. So, if it is 8 partitions, according to this scheme, every partition should have equal size. So, 64 by 8. So, size of each partition will be 8 kilobytes. Okay. This partition P1 will be 8 kilobyte. This partition P2 will be again 8 kilobyte. Okay. You will have 8 partitions, for example. This 1, 2, 3, 4, 1, 2, 3, 4, 5, 7, 8. Yeah. So, each of the size of each partition is 8 kilobyte. Assume that operating system is residing here. Now, 7 partitions are free. Now, assume that. Now, here what is the advantage with this technique? The advantage with this technique is it is possible to accommodate 7 number of processes to reside in memory simultaneously. Now, let us see. We have a job J1. Okay. Suppose the size of this job is 1 kilobytes. Okay. Now, what happens? Now, because all of them are of equal size, it is okay. First fit is always used here, wherein whenever you see any empty partition and the size of this partition is greater than or equal to the size of this process, then only job will be allowed to enter into this partition. So, job J1 will be setting here, which is of 7 kilobytes. Now, the size of the partition is 8 kilobytes and job J1 will take only 7 kilobytes. Okay. It takes only 7 kilobytes. Now, here 1 kilobyte of memory is wasted. We call this 1 kilobyte of memory which has been wasted called internal fragmentation. Now, similarly, we have another job J2. Suppose the size of this job is 6 kilobytes. Now, will it be allowed? Of course, job 2 is also 6 kilobytes, but here what happens, 2 kilobytes of memory will be wasted. Suppose I have another job called job J3, okay, job J3, and the size of this is 8 kilobytes, so 8 kilobytes will be accommodated. Job of J4 is also 8 kilobytes, okay, J5 is also 8 kilobytes. Suppose I have job J6 which is also 8 kilobytes, for example. Now here in this case, in these 4 cases, internal fragmentation is 0 because there is no space left which is internal to the partition. Now assume that there is another job called job 7, okay, which want to enter into this, which want to be loaded into this memory, and the size of this partition is, the size of this job is suppose 10 kilobytes. Okay. Now here the condition violates. Okay. In this scheme, the condition is the size of the partition, should be greater than or equal to the size of job or process. Now because here the condition gets violated, okay, here the size of partition is 7, the size of this partition is 8, okay, and 8 is not greater than 10, so it cannot be loaded. Now this entire partition is wasted. Now when you see here, okay, 8 kilobytes, actually total memory which is available is 8 kilobytes here, 2 kilobytes here, 1 kilobyte here, which is equivalent to 8, 9, 10, 11 kilobytes is available. Total memory available is 11 kilobytes, but the job whose size is 10 kilobytes is unable to allowed to enter into this partition. Okay. So now here, because the size of the partition is fixed here, okay, it cannot be loaded. Here in this case, the external fragmentation is 8 kilobytes. Okay. So here you will have, if this job comes, then external fragmentation is of 8 kilobytes because this process cannot be allowed to execute. Now we have to find out. Now the problems can be asked. Okay, they'll give you job and their arrival time and size of the, and also I will ask you to find out the total fragmentation. The formula for total fragmentation is total internal fragmentation plus total external fragmentation. Okay. Now total internal fragmentation is 1 plus 2 plus total external fragmentation here is 8. Total fragmentation is 11. So 11 kilobytes of memory was inefficiently utilized. Even though the total amount of memory is 11 kilobytes, we are able to execute a process whose size is 10 bytes. Okay. Now the advantage of this scheme is CPU utilization is efficient, effective. Memory is also efficiently utilized, and multi-programming is here because it is allowed a number of processes simultaneously into the memory. But of this scheme is, if the size of the process is greater than the size of the partition, okay, it is not allowed. Okay. Now how do you solve this problem? Again, this problem is again solved by dividing the memory into fixed numbers. The size of each partition is of variable size. Okay. Meaning, I'll take same example. Suppose 64 kilobytes of memory is there. Okay. When 64 kilobytes of memory is there, now suppose 8 kilobytes is used already by the operating system, and remaining 42 bytes. Okay. Now you might be having one of 8 kilobytes. Okay. Another will be of 16 kilobytes. Okay. Another will be 24 kilobytes. You can have 10 kilobytes or 6 kilobytes. $10 kilobytes, for example. Okay. So 6 KB and 10 KB. Now it means the number of partitions are fixed, which are 6. The number of partitions here are fixed, and size of this partition is also fixed, which is 8 kilobytes, 16 kilobytes, 24, 64, and this. Now the problem with this, the advantage of this scheme is, earlier this job J7 was not allowed, but now this job has been allowed. But still there is problem with this approach. The problem with this approach is, you may have internal and external fragmentation here, okay, which is one case, and here the main problem is what happens if the size of the maximum partition, okay, is here 24 kilobytes, and if the job size is 25 kilobytes, again it will not be accommodated. Okay, this is also one of the problem with this scheme. Okay. Now because of this variable number of, because the size of the partitions is variable, then we go for different algorithms which slot to be given for process. For example, suppose I have a job, okay, you take an example of job which is 7 kilobytes. Okay. Now I have to take a decision here. This job 1 which is of 7 kilobytes, okay, can I make it sit here or here or here or here or where? Here I cannot. Okay, if I make it sit here, only internal fragmentation will be 1 kilobyte. But if I have taken a decision here, so what happens? 8 kilobytes will be wasted. Here 16 kilobytes will be wasted. Now assume that if there is another process of 6 kilobyte already occupied this, okay, then again where I have to where I have to allow another process of size 7 kilobytes. Okay, again problem. So here I have to take one decision. So in order to take decision which job will go and which partition, we run different algorithms called best fit, worst fit, next fit, or worst fit. Okay, these are the different algorithms which we will use in this scheme. Okay, so what is best fit? Here we will see best fit means it should have minimum. You have to select among all the available partitions which partition leaves less internal fragmentation. Then we will see next fit. What do you mean by next fit? Now assume that now whenever you do best fit, okay, we start from the beginning of the memory. Okay, assume that we have allocated, this has been allocated, this has been allocated, and I have to take, suppose this has not been allocated and this has been allocated. Okay, now the last allocation block is suppose here. Okay, and I have a process and have a process whose size is 8 kilobytes. In using next fit, okay, the algorithm, how this algorithm works is it will allocate a new job, okay, whose size is 8 kilobytes, where it will accommodate in next fit. Okay, it will see what is the last allocated block. The last allocated block is 6 kilobytes, so it will go to this, and from this pointer onwards, what are the available partitions? It will go for it will look for a partition which is big enough to accommodate this, right? But whereas in first fit always, irrespective of the last allocated block, assume that the last allocated block is 6 kilobytes. Next fit will start searching not from the last allocated block, but it starts searching from the beginning of the partition and looks that is there any partition which is big enough to accommodate this process. Okay. So first fit and next fit, they are same, but the starting point for these algorithms are different. Okay. Next fit will start from last allocated block. First fit will always start from the first partition itself. That's why the name first fit. Okay. Best fit always ensures that there should be less fragmentation. Then you have worst fit. In worst fit, you have to allocate a partition in such a way that internal fragmentation should be more. Okay. Now there are few cases in which worst fit is not worst, okay, which we'll see in third scheme of memory management called dynamic memory allocation, okay, which we'll see in the next session.